All right, welcome everybody. We're so glad you're here to join ScaleFlux and Xinnor. We are happy to share some of the work we've done on high performance NVMe RAID solutions. I apologize if you hear a little bit of an echo. This is not in fact my pool or my house. I am actually in a very empty room. So there's a little bit of reverberation, but I apologize for that. Let's get started. We're going to go ahead and I'm going to toss this over to my friend Davide at Xinnor, and he's going to give you a brief overview of their technology and how it's enabling high-speed NVMe RAID solutions. So Davide, take it away.
Thank you, Kit, and very nice pool indeed. Unfortunately, I don't have it behind me. Okay, good. So my name is Davide Villa, as Kit just said. I'm the Chief Revenue Officer at Xinnor, or the CRO, and the R might stand for RAID, if you want, since this is what we do. So let me start sharing some information about who we are, and then about our technology, and finally, Kit will show the work that we did together, showcasing how our technologies complement each other. So let me start by telling you who is Xinnor. Xinnor is an Israeli company. We are a very young company because we were founded just 1 year ago. But differently from most of the startups, we leverage more than 10 years of experience because the company originated from the sales of Radix. And while selling Radix, the founder of Xinnor, they managed to keep all the international intellectual properties, which now belongs to Xinnor. And our mission at Xinnor is to develop the fastest RAID engine in the market. We're a small team. We're about 40 people and growing. Most of our teammates are in development. They are very high-level mathematicians and storage engineers. And we are building our network worldwide. We already have 20 plus partners and more than 100 petabyte of data protected by our RAID engine. And we like to partner with great companies, ScaleFlux being one of them. And by the way, just recently we have been awarded the Best of Show at Flash Memory Summit in August for the most innovative customer implementation together with Western Digital and BGFS. So what do? First of all, we do RAID engine. That's the core of our technology. That's what we work day in, day out to optimize and get the best performance. But why do we need a RAID engine for NVMe? The reason is very simple. So if you look at today, the option that you have when you want to deploy NVMe, you can either use hardware RAID, traditional hardware RAID, but hardware RAID is limited by what the ASIC can deliver and by the PCIe bandwidth. So at the end of the day, you will be limiting performance if you have more than 6 NVMe under hardware RAID. The other option is to use open source software RAID or a proprietary permutation of the same open source software RAID. The limitation with MD-RAID is the architecture itself. MD-RAID is designed to lock one single stripe to one single core. And by doing that, it creates a spike of load on the specific core, which translates in a bottleneck in the performance. So what? The customers are not left with many options. They can try to implement a very expensive RAID 10, but with the RAID 10, you're wasting 50% of the capacity. Or you can use open source software RAID in RAID 5 and RAID 6, but in this case, you lose in performance because, as we saw, MD-RAID is not optimized for performance. So you buy expensive NVMe, and at the end of the day, you don't get the performance that you expect from them. Or the alternative, the third option, is to have no RAID at all. And in this case, if you lose one drive, you lose your data. So our architecture is very different. So we, first of all, we leverage what you already have in your server. So we leverage AVX technology, which is available on every x86 CPU. And then we combine it with a lockless data path. Lockless data path means that we dynamically map the stripe to the CPU core. And by doing that, we avoid spikes of load. We can equally distribute the load across all the available cores and maximize the performance. So at the end of the day, the key selling point of our solution are performance in normal operation, primarily when you start mixing read and writes. Even more performance in degraded mode. People are implementing RAID because they need data integrity and protection. And you should expect that when you buy a RAID engine, it delivers good performance in a trouble time, like in degraded mode. And then finally, we do all this by using very little CPU. We take just 2% of the system CPU to calculate the checksum. So performance is the key benefit, but it's combined with flexibility. We support any type of RAID, we support any capacity, any type of drive. No need for extra hardware, so it's a software-only implementation under Linux. No need to waste a precious PCIe slot. On NVMe server, there are not that many. You might want to keep it for your network card. Because at the end, we use the system resources, very little memory because we don't have a cache, and just 2% of the system CPU for the checksum. And we have a technology that enable us to handle single IO errors, and that can happen when you have SSD connected through the network. So in this case, this technology, which we call a fault tracking system, enable us to work not only with local drives, local SSD inside the server, but also with a network attached SSD in NVMe over Fabric type of implementation. And don't trust my word, give it a try. You can go on our website, or you can follow this URL and request a trial license, and our engineers will be more than happy to work with you in getting the best possible performance. So with this, let me hand it back to Kit for
All right.
ScaleFlux Intro.
Thank you for that. Let me pull up my sharing here. All right. Everybody can see the presentation there. Well, we need to do it better here. I mean,
not any longer.
Everything's got to go wrong on a live webinar, right? Let me. Such is life. All right. So while I'm pulling this up, let me briefly introduce ScaleFlux. So ScaleFlux is a NVMe SSD vendor. We have our heritage in computational storage. So we come from a computational storage background, and that means that we combine fast NVMe storage with compute functions that can operate on the data without having that data leave the drive. And so one of the key features that we have in our current generation of products is a feature called transparent compression. And what this does is it compresses data in the controller after it arrives to the disk and before it arrives in the media. And then it decompresses data as it leaves the media and it gets sent to the host. So we call it transparent compression because the host doesn't know that it's happening. And so we'll get to why we would do such a thing in just a moment. So let me go ahead and share one more time here. All right. Hopefully this will be better. Okay. So first, let's take a huge step backwards. And not talking about RAID, let's just talk about something that applies to any SSD, and that is, what is the root cause of latency? And so an SSD controller really at its core has to translate from PCI Express with NVMe as the protocol to NAND. So an I/O that is 4K bytes ends up being distributed, or any amount of I/O, and just being distributed to one or more NAND die. Okay, and if you look at the NAND die, NAND can really do three things. It can do a read, it can do write or erase, but it can really only do one of those at a time. And technically it's per plane, but let's just use die because it's a simpler concept, right? So if I have a die that's busy programming, it can't be reading, it can't be erasing. If I have a die that's reading, it can't be programming, can't be erasing, and so on. Now there are tricks controllers can play. They can suspend program a number of times to try to let some reads through, but fundamentally, every operation in NAND is blocking. And so if you have some I/O and it needs to get to some data on one of the die, then it sort of locks out all the data on that die while that operation is happening. And what happens is that those operations that need that data end up queuing up to that NAND. And so we end up forming these queues. You can think of it as queues into the NAND. So writes and reads kind of stack up. And the more pressure or the more simultaneous I/O we submit to the drive, then the more we're going to have to queue operations into NAND. And that's really where latency in an SSD comes from, fundamentally, from whether it's a SATA SSD, an NVMe SSD, any NAND-based SSD. This is the fundamental driver of latency. So we do transparent compression, and how does this help? When we think of transparent compression actually as an accelerator, which is kind of opposite from what most people think of compression. People think, oh, CPU is a trade-off between slowing down and having smaller data. But when you do transparent compression in hardware at the full speed of an SSD, it actually acts as an accelerator. And let's try to understand how that happens. So if I have, let's say, a set of writes that are queued to my NAND, if I've compressed that data from the host, effectively what I have is half the writes being queued to NAND. And if I have half the writes that I would otherwise need to use to program the data, I can open up more of that NAND bandwidth for reads. And so what ends up happening is I can just service more reads and I can get them done more quickly, and that lowers latency, especially at the tail. So transparent compression is all about reducing read latency in the face of write operations. And we have some data here to share. This is looking at our CSV 3310. And what we're doing here is we're ramping up from left to right on the chart the amount of 4K random read IOPS we're trying to get out of the drive, while we have a constant 25K random write workload. So those writes sprinkled into the drive, these drives are being asked to do 25K write IOPS and then also service reads. And what happens with transparent compression is because we're taking that 25K IOPS and we're compressing each of those, we have a much smaller chance that reads get interfere, writes interfere with those reads. And so when we look at our P99 latency, we see that in our linear area here from, say, 400K IOPS to about 1 million IOPS, that slope is much smaller than you would normally see in an SSD that has to write all of the data that was sent to it. And so that's, in a nutshell, showing you what the power of this of compression is. But really, what does that have to do with RAID, right? So we're talking with Xinnor, and now we're talking about details of latency in SSD. Well, let's bring this back and let's think about what are the operational states of a RAID. And here we're considering RAID 5. Obviously we want to operate in normal mode, And basically, we really want low read latency while we have that RAID 5 write workload. Now, keep in mind, it's not just writing data, it's writing parity, so it's a little bit of extra stress on the drives to add that protection. And we just want really great performance. So it doesn't matter if it's a RAID array, frankly, or any other I/O application. We want to get those writes out of the way from the reads. But in the case of RAID, this is particularly helpful because we can ameliorate some of the issues with the extra write burden that the protection adds to that. But really, RAID's all about how do you do in the two kind of states of degrading and reconstructing, right? So when you're degraded, we still want low latency, right? We never want to give that up. But the problem is now we have fewer die to work with. And so what compression is going to do is kind of give you that little bit of wiggle room to be able to work with fewer die and not have this severe of a performance impact. Then lastly is the reconstructing state. And this is obviously the most stressful, right? Because not only do we still want our I/O to be fast and low latency, we still have fewer die to work with because we haven't rebuilt the drive back into the array. But now we have this introduction of this reconstruction traffic that's going on within the RAID array. So it becomes even worse, right? So not only we have fewer data to work with, we have more data that we have to keep moving around. So what transparent compression is really going to do here is it's really going to help all of those states by lessening that write burden and getting reads done more quickly. And so I think there's no better application to demonstrate this than Aerospike. For those who are not familiar with Aerospike, it's a very high performance Flash native NoSQL database. And so what it effectively does, it keeps the whole data set in high-speed NVMe storage. And what that does is gives you nice uniform latency access to huge data sets. So it doesn't matter really how big my data is. It's all sitting in Flash, so I can get to it all very, very, very quickly. It's quite an interesting solution. And what we did is we built a xiRAID RAID 5 array. We used 5 3.84 NVMe SSDs. These are our CSD3310s. Then we used the Aerospike certification tool to simulate the Aerospike I/O workload. And so ACTs, they've got their nomenclature, and one of those is the X level that you run. And so we ran at 500X, which means that it did 500,000 write transactions and 1 million read transactions per second. So what ACT does is you say, I want to run this workload on my storage, and I want to measure my performance because this is a fixed amount of traffic, right? And what do we want to see out of this? Like, why do we care, right? So what we want to see is this workload, the simulated database workload, and we want to see that when the RAID array goes into the degraded and reconstructing states, that the host doesn't notice. The host doesn't see drop in throughput, and the host still enjoys similar latency or as good a latency profile as it was seeing previously. So let's look at throughput and what was achieved there. Now, this is a measure of a very long, many hours of the test. And in the beige bands here, we show in the white, the RAID is operating in its normal condition. In the dark beige band, that's the RAID arrays are operating in a degraded state. And then a light beige band, it's operating in the reconstructing state. So the two blue lines there, you can see the one at the top there is the read throughput, and it is very steady, it's a little over 5 gigabytes per second. Similarly, we don't see any variation in the write throughput. We're still at 1.5 gigabytes per second, and this is through degraded and reconstructing states. And that purple line there is the CPU utilization. This is for the system CPU, so the kernel side CPU utilization, and we see that it remains very constant, very low. Actually, even drops a little bit during the reconstruction phase. So check mark 1 with the throughput looked great. We didn't see any variation. But what about latency? So ACT has a very interesting way to look at latency. And so it's really concerned with the amount of transactions that exceed a millisecond or certain thresholds. So one of the big goals of ACT is that no drive should have the percent of transactions exceeding 1 millisecond be greater than 5%. In other words, I can only have less than 5% of my transactions exceeding a millisecond to consider a passing result at that level of pressure that we apply. And remember, we said 500x, which is 500,000 writes transactions and 1 million read transactions at the same time. And so what we can read, how we can read this is these are the percentage of transactions in red that were greater than a millisecond. And we see that is very, 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 very low and well below the passing threshold for ACT. But what's really interesting is, again, we have the dark band for operating in degraded state, and we have the light band for operating in reconstructing state. We hardly notice the difference in the latency in terms of how many transactions coming back a little bit longer. You see some very almost imperceptible difference in the reconstructing state, none in the degraded state, and we return to a very nice, low, steady number here, which is great. So again, we saw from the throughput doesn't change. We saw latency, very little changes there. This means really that if a drive drops out of the array in my Aerospike solution, I'm going to go ahead and be able to reconstruct a drive into the array, and I'm not going to have to take that node offline. I'm not going to have to do any rebuilds. I'm not going to have to send data over our network. I'm going to be able to keep that all self-contained while meeting my SLA goals that I have set around that database. So again, to reiterate that, so we're using xiRAID with ScaleFlux 633310 with transparent compression. What we're doing with this combined solution is improving node resiliency. So we're giving consistent low latency performance even when the array is in degraded or reconstructing state, which I think is really, really critical. And we could start imagining solutions around, perhaps if we're in a triple application environment, maybe we can add RAID arrays there at the node level and go a dual replication because we can tolerate failures in DIS much better. And we can avoid a lot of network traffic, a lot of network sizing can go down, and a lot of rebuilds can be avoided. So there's a lot of things, powerful opportunities here with this combined solution. And lastly, we all want to tease this a little bit. We're teaming up also with RackLive, a system integrator, to do some testing with Postgres. So we're gonna be able to demonstrate just like we did with Aerospike, some of those values as they pertain to Postgres. So stay posted for that. And with that, I will turn it over for any questions we might have.
So I see in the chat there is a question about Xinnor know-how. Is it just AVX instruction as accelerator? Yes, I oversimplify, obviously. It's not just that by using AVX instruction you can get the performance that we got. There is a combination of how we use AVX in combination with our lockless data path. So it's clearly more complicated than what's written in the slides. But yeah, fundamentally, we through AVX, we don't need external GPU because we get 50 gigabytes per second for checksum calculation from every core. So that's more than sufficient. Okay.
Any other questions?
That's probably for you, Kit.
Does transparent compression have any performance impact in the SSD? So that's a complicated question, interesting one. So the way that we implement transparent compression is in RTL. So it's a hardware engine. So the latency on that's very, very, very small. It can be hidden on the write through some pipelining effects. On the read side, it varies a very, very, very small percentage of the total T-read time for NAND. So it's, I would say, nearly imperceptible. The secret to that is just doing it in hardware. It's not a CPU-based compression in the ARM cores in the SoC. It's actually done in dedicated hardware. The interesting thing, though, about transparent compression is that you don't need a huge compression ratio to really get a lot of benefits. In fact, I'd say most of the benefits extracted at like 2 to 1. So you get the biggest benefit going from incompressible data to 2 to 1 compressible data. So even lightly compressible data, say like 1.25, 1.5 to 1, has huge endurance benefits, huge performance benefits. And it kind of makes sense. If you think about a read-intensive versus write-intensive SSD, what's the difference? The difference is 20% extra over-provisioning. So if you can get effective over-provisioning to the degree of 30 or 40 more percent just through compression and saving just that little bit of space, you're going to have huge benefits in endurance and performance. So it's quite nuanced and quite interesting. You don't need a huge compression ratio to achieve pretty amazing results there.
Okay, that's a tricky question because I believe you you explain it somehow. So
I can kind of take this one. So because of the transparent nature of the compression, the Xinnor software does not know, right? It doesn't need to know. It doesn't care. It sends its data to the drive. It manages the drive on its LBA basis, and we're kind of behind the scenes squeezing that down and then using that to realize the benefits. So there's really nothing that the Xinnor needs to do special, or any application needs to do special to take care of transparent compression and get these performance advantages that we talked about.
So regarding Xinnor, is it possible to extend a RAID, to downsize a RAID? Yes, so we support restriping, so you can add additional drive to the RAID group. You can also change the RAID typology, moving from RAID 5 to RAID 6. So the RAID engine will take care of recalculating the checksum and rebalancing the data.
Okay. Benefits when workload pattern changes. Do you want to answer from a RAID perspective first, or?
Maybe I can answer from a RAID perspective. You can elaborate a bit on compression. So from a RAID perspective, sequential, it's easier than random, like for everything when it comes to SSD. But actually, that's probably where we excel more than anybody else. In reality, we provide even better performance delta when you operate random operation, whether they are random read or random write. And maybe you can elaborate a bit on the compression.
Looks like there's a kind of some clarification also there about hot LBAs. So hot LBAs, you can think of an SSD as being LSM kind of structure. It just rewrites data in a different location and overwrites old data. So hot data is not a huge doesn't have a big impact on an SSD, whether data access is concentrated in kind of a shorter band or a wider band. QoS, again, if you look and you zoom out and you look at that one, you send just a single read to the drive. You got a T read on the order of 45 microseconds to 60 microseconds. The decompression is going to happen on low single-digit microseconds. So it's really going to be 1%, 2%, 3% of the overall time on a per IO basis. But the magic really is in those concurrent workloads where we have writes going to the SSD, and getting those writes out of the way of the reads has a huge benefit on QoS. We saw that chart earlier where our tail latency is not going to scale nearly as high as we get towards our saturation point for random read, and that's really just because we are getting those writes out of the way, and so that has a much bigger benefit to QoS than any very small penalty in decompression latency.
So there is one more question for myself. What latency impact is there on external network SSD added to the RAID? The answer depends on the speed of the network. So we have experience with different type of network attached SSD. We see best performance can be achieved with RoCE Ethernet technology. But we also have experience with TCP connectivity, and what we see is that from a RAID perspective, there is no penalty whether you use them directly attached to the server or through the network. There is a light penalty related to the network itself. But in some situations, we're working on our next generation product where we will move out of the kernel and support SPDK libraries. In that case, we see nearly zero penalty from operating the drive from the network.
Okay, so I think we're through the questions, and if you have any more, you think of anything, I'm sure on behalf of Davide, be happy to answer on the Xinnor side, and of course, I'm happy to answer through LinkedIn or wherever you may find me to answer any questions you might have. So, well, again, I want to thank everybody for attending. Really excited about future work, the current work, and also the future work we're going to be doing. So stay tuned for that. And with that, we'll say good night and good morning, or where you may be.
I think it's wine time here in Italy, so
Late
the wine.
Go ahead and call that a wrap. Thank you so much.
Thank you, Kit.
Everybody.